I hope all of you have submitted your homework one. I got few emails and then few paper submissions. So that wraps up our discussion on chapter 1 and 2, which together is like module 1. And I just want to remind you about the first exam on March 6th, which will be 80 minutes starting at 5:30 going until 6:50. And it will have four problems, one from the first unit and three from the second chapter on scalars, vectors, and tensors. So it is just based on whatever we have done so far. All the discussion that I'm going to do today and on Thursday as well as the next Tuesday is not for exam 1. It will be tested in later exam 2. Okay. The programming assignment, the homework that you submitted today is worth 5%. The programming assignment is also worth 5%. I made that change, and that is coming up on next Tuesday. So I'll open up a Canvas submission link. You just have to upload everything. What I suggest is that you create a PowerPoint file in which you put your code, the description, as well as the screenshots of your output so that I can look at it. And if I look at your code and I maybe want to further examine it, I might request you for the source code, or you can just go ahead and submit the source code file. That is submit separately as well, so that I'll have the code, and if I want to see. Okay. Any questions regarding this submission? No? You're okay? All right. Okay, so if there are no further questions related to these two announcements, I want to start with the next topic, which is in our textbook, coming up as chapter 3, kinematics of deformation. So throughout the discussion so far, we were not making any reference to a particular material or any particular physics law. All we were learning is how to work with tensors. Like we were learning index notation, summation, manipulation, calculating matrices, or the different properties of orthogonal matrices, eigenvectors, coordinate transformations, and so on. So moving forward, what we plan to do is to use this knowledge to study continuum mechanics. This is where the course in effect starts to become a real continuum mechanics course. All the while it was more just mathematics. So now we want to use those tools to go further. And in doing so, in the very first lecture I talked about, if you have a body, you can apply a load, and a load is a cause. And what does it lead to? What does the load, when you apply a load on an object or a fluid or any kind of system, what is the response? Deformation. So there is a change in shape and dimensions, which is what we call deformation, which is an effect. So in this unit, we are going to study description of how bodies deform. Kinematics is essentially the description of shape changes and how to use mathematics to express those shape changes. That is the focus of this entire unit. Again, we are only going to focus on deformation. We are not going to worry about what causes that deformation. Like if I have a object in my hand, I can put it in an anvil and crush it and make it compress it. Of course, the loading part is essential to causing the deformation. We are going to study how to describe deformation without studying about the loading, which comes in the next unit on where we talk about conservation laws like force conservation, energy conservation, and so on. So for now, focus on this. Okay, how to describe deformation. That's the goal. To do that, we have to introduce some concepts as we usually do. The first concept we want to introduce called the continuum particle. We want to introduce a concept called the continuum particle, which is like saying, let's say you have an object or a body and we choose a particular point. Okay. We call that a continuum point in the sense. So this body, we want to use the word B to denote that, and the surface we denote it as delta or partial B. And this point here P, which is our continuum particle, what do we when I say I think of particle, what is the notion that comes to your mind? Just tell me what you think. What is a particle in your opinion? Before seeing this course, what have you thought when you said particle? One molecule. One molecule. Any other perspectives? What is a particle? A molecule which can. So you are thinking only like an individual molecule, right? No other thoughts, like you haven't encountered the word particle in any other context? So the word particle is actually quite ubiquitous if you think about it. If you go out and find a nuclear physicist and ask him or her what is a particle, what will their answer be? Can you guess? What is a particle for them? It's like protons, neutrons, quarks, gluons, whatever they deal with within the nucleus. For them, that world is within the nucleus. For them, particle means those subatomic particles. If you find somebody who does classical physics like spectroscopy, for them, individual atoms or individual molecules are the ones they deal with. Like you said, a single molecule. For them, that a particle is like a molecule. For somebody like me who works with aerosols and little particles, for me, particle means nanometer sized or micrometer sized dust particles that float around in the air. To me, that is a particle. To somebody who works with mesoscopic systems, who's like where, suppose you are working with granite, sorry, not granite, concrete. You have the sand particles, they are big, like millimeter size to centimeter size. Right? For you, particle means completely something else, where it is centimeter sized object. Now remember, we started with nuclear physicists. For them, a particle is like 10 power minus 40 meters or something. For you, it's 1 centimeter. It's such a big disparity in what you call particle and what they call particle. And if you keep moving further, somebody who plays a sport, for them, their particle is of the size of a 10 or 15 centimeters, like a ball, like a baseball player or something. So the word particle itself doesn't have a universal meaning. Everyone uses it in their context. We are going to invent our own context, which is to say a continuum particle is a point in a material at which all relevant physical quantities, which may be scalar, tensor, or vectors, physical quantities can have a well-defined analytical value. This is again my own definition. The book will have slightly different wording. Okay, this is again in section 3.1 that I'm talking about. So we are talking about a continuum particle. It is a material point in which all quantities that you care about, like density, strain, stress, force, velocity, anything that you care about is well defined as a tensor field or as a field in general. And the continuum particle You can think of it two ways. It's a mathematical point at which quantities are well defined. That's what I just said. Quantities are defined. You don't have to worry about what is it made of. Okay, here, not worried about what is it made of. You can also think of a continuum particle as a small representative volume which has enough atoms to define a smooth average for relevant macroscopic quantities. Like if you think of density, for example, in the very first lecture, we talked about how density at a point, if you keep shrinking down, at some point that space is the space between two atoms. It's really not defined at that level. So you zoom out just enough so that you can define a density, and for defining that, you need enough number of atoms so that you get a convergent average for density, velocity, and so on. So you can think of it just as a mathematical quantity. It's a point. At that point, all my quantities are defined, end of story, move on. Or you can also think it's a point which is a teeny tiny volume. It's so tiny that when I zoom out and my system scales of interest is some length, okay, that length is for us usually of the order of at least microns or millimeters or bigger. At my length scale of interest, the internal details of this point are irrelevant because those internal details are of the scale of atomic dimensions. Remember, we defined a Knudsen number and defined it as the mean free path divided by the length scale of interest. For this course, all the time, this number is always less than 1. So we just say that it's a tiny point. It has an internal structure which I don't care about. For me, it's a point. Outside, I'm standing outside the point. Why do I care what's the internal structure of them? So this is also one way to think about it. So whenever we talk about, here's a point in a material, and let's say we apply a load at that point. What is the response to load? Deformation. And what is deformation? Change in size, shape. Okay, when you say change in shape, at an atomic level, what is happening, you think? More and more atoms. More and more atoms or what? You should tell me a complete sentence. I don't want to complete your sentence. Atomic shrinkage. Can atoms really shrink? No. Should be under some pressure. Change in orientation. I'll come back to you. It's not. We are not getting anywhere, so I wanted to switch. Yeah. Change in orientation of what? Atoms are all dots. What orientation can a dot have?
They can get closer and further apart than away.
So what you're talking about is not the orientation of a single atom. It's like a group of atoms which have a certain configuration. When you apply a load at that point, what you're changing is that changing the configuration of the atoms or making them come closer. That's what I think you meant by shrinkage. It's not the atoms that are shrinking. It is the space between the atoms that are brought closer. So in a very small percentage. So if you have, say, for example, a material and you apply load, what is compression? Compression is the atoms getting a little bit closer. And why do you have resistance to compression? Why does any material have strength in the first place? It comes from the atomic nature of matter, that atoms don't want to be squeezed onto each other. They resist, and that's what you feel as a strength. In order to get a certain strain, you have to apply a certain stress, and that stress varies between material to material. But all materials have some strength which comes from their chemical composition and quantum nature, which of course we don't want to go into. But that is the origin of their strength. So a deformation at an atomic level is basically a rearrangement of atoms which make them come closer or go further. And what we think is that this material point P, if you apply a load at that point, it undergoes a deformation. We just quantify the macroscopic change in its quantities without worrying about the internal atoms or what they do and so on. So when we talk about a compressive strain at that point P, the implication is the atoms have been forced to come closer, but we measure the strain as change in dimension in a macroscopic sense. Or how do we measure density? It's the mass of material per unit volume. We don't worry about atomic number. We just worry about how many grams were there in a certain volume. After the deformation, how many grams are in there? What is the volume before deformation? What is the volume after deformation or after application of a certain loading? Okay. So this material point might look like a very simple concept, but the idea is whenever we do loading or any kind of deformation operation, we are assuming that this point still always has enough atoms so that a quantity can always be defined and its quantity value can be changed, reduced, or increased, and so on. Okay, it's basically a bunch of atoms. And you also should read up this section because the book has a nice discussion about this two viewpoints of this. What is a continuum particle? It talks about some stories as well. So I want you to read that. Okay. So for those who came late, next Tuesday your programming assignment is due, and next Thursday exam. Okay. And a request from me, please come to class at least 2 minutes before so that don't enter the class en masse after the class started. All right, next is deformation mapping. Deformation mapping. So this is, I would advise you don't have to take notes because this is sort of the core concept in this whole unit. If you miss the bus here, it's very hard to catch up. Just let's talk, okay? Don't spend time writing now. So suppose you have a body or a material in some configuration. When we are describing deformation, deformation is always a relative description. It has changed in shape relative to what it was. I can say that I have put on weight. I should also tell you how much I weighed 10 years ago or 5 years ago. It's always relative. Change is relative, right? So when we talk about deformation, you need to think in terms of configuration. That is, what is configuration? It's basically the initial shape, or let's say shape at a given instant of time. And that configuration changes, that process is what we call deformation. So to describe deformation, you need two. You need at least one configuration which you want to call as a reference configuration. And usually, what do we do in the lab when we do, suppose you're doing tensile testing, what is your reference usually? It is the dimension of that component before you started doing any loading, right? It's most often the shape of the material sample, material sample, not just material, it's like you make a little sample, shape of the material sample before any load was applied. It's the initial shape of the material sample. Okay, so this shape, okay, I'm just going to draw it like a potato here, and I want to denote this shape as B naught, and I'm sorry, surface is sigma B naught and shape is B naught. Not meaning initial. Okay, and we'll select a point P in this material, randomly selected continuum particle. Okay, now this point P, suppose you have an axis 1 and axis 2. With respect to this coordinate system, let's say it has a position vector which we'll call uppercase X. Uppercase X. Now we do our loading. Loading leads to change in shape or deformation. And let's say the deformed shape looks something like this. So this solid line is the initial shape, and this dashed line is the deformed shape. You can call this solid line also has the reference configuration, and the dashed as the current configuration. Right? It's almost like saying, here is here is an example of a material that's about to fail. It's my cell phone cover. If I call this as a reference configuration, I'm pulling this apart. The rubber that is holding the frame is deforming. I'll call that like a current configuration. With respect to my initial shape, I'm talking about this thing I'm pulling apart. It's basically changing shape. So it's a matter of choosing one as a reference, which is most conveniently the one before any loading, because before loading you know the shape. So let's choose that as the reference. The real question is, after loading, what is the shape? Okay, with me so far? Yeah.
What's B naught again?
P naught is just the kind of a label we give to the initial shape of the object. The after deformation, if you want, you can call it final shape, or if you say reference is current, sorry, reference is old, deformed is final or current. We'll call that as B without the naught, and its surface is partial B. Naught is just to denote it was the initial, that's it. Okay. All right. The whole idea of shape change, how do you measure shape change? How do you define shape change? Intuitively speaking, what is a shape change? Change in what about the body? Structure and design. What is structure? What is structure? Appropriate shape. So we don't have a beam running through here. Like suppose you had like a beam that is going from left to right. Okay. Due to excessive loading from above, let's say the beam starts to sag. Not a lot, but a little bit. Okay. What do you mean by the beam is now deforming? A point which was previously at this level has now dropped down a little bit below due to the loading. Shape change is nothing but a mapping of points from one configuration to another. A point which was originally here is now moved on to here because of the loading. That is what literally when you stretch it, you can do the experiment where you have a rubber band, you mark 2 points with a pen, and you stretch it. The 2 points will be the separation between them will increase. That is literally what deformation is. You are having increase in separation between them, so there is a change in length, right? And we go back to engineering definition where it is change in length divided by initial length. Shape change is nothing but the mapping of individual points from one location to another. They went from a reference location to a new location. That's what deformation is. So I'm going to write deformation at a very basic level is a mapping of which point ended, or I shouldn't say which point, is a mapping of how continuum particles are moved to a different, or the particles are moved to different locations. That is the point that was here, due to the stretching, it's now gone to somewhere else. It's the same continuum particle which has now been moved to a new location. Okay, that is what we call deformation at a really basic level. It is a mapping that connects the position of a point in a reference configuration to a current configuration. So I'm going to write a deformation is a mapping. I'm going to give you some break to write up all this. The mapping of points from, I'll say the reference instead of a reference, because reference can be only one. That's why it is the reference, right? From the reference configuration to the current configuration. I'm also using the again because if at a given instant there can be only one current configuration, for that moment it is unique. If you go to the next moment, you can have a different current configuration. So it is a mapping of points, how points go from one location to another as loading is done, or as they go from reference to the current configuration. Okay, and now we are going to turn this into math, but before that I'll give you a break to write up this part. I also again I'm starting to indicate the section number. By default, I imply that you should go home and read these sections so that I'm trying to present that content in a lesser time. you read through the entire text, you will learn a little bit better. And when you see the lecture plus the textbook, it will make much more sense. Okay. So please do the reading. Keep reading the textbook as I talk about these topics. Okay. Please tell me when you are done writing. Good. Is anybody still writing? Good. Okay. Almost done. So I'm just reading a sentence, couple of sentences from section 3.2. This is the first sentence. A body B can take on many different shapes or configurations depending on the loading applied to it. We choose one of these configurations to be the reference configuration of the body and label it B0. The reference configuration provides a convenient fixed state of the body to which other configurations can be compared to gauge their deformation. Any possible configuration of the body can be taken as this reference. Typically, the choice is dictated by the convenience to the analysis. Often, it corresponds to the state where no external loading is applied to the body. So before you start your experiment or your deformation, that configuration is the most convenient choice. Okay. All right. Can we go? All right. So the position of P, the continuum particle, is denoted or in the reference configuration is denoted as X bar uppercase. We are going to use uppercase always to denote reference. Okay, that is just a given from here on. And we just write X bar equal to X of the point P to denote it's the position vector for point P. Okay. I'm just going to write this from the book so that I don't misquote it. The deformed configuration, the deformed configuration occupied by the body is described in terms of a deformation mapping. We'll call it phi. It's a deformation is a mapping, right? So now we are calling the deformation mapping phi that maps the reference position of every particle X that is for every particle that resides in the body, we'll denote X like a position vector to its deformed position deformed position lowercase x. From now on, lowercase x is reserved to denote deformed position x as follows. We write x is a function of uppercase x. It's a mapping. That is, phi is a scalar valued function which takes a vector as an input and gives a vector as an output. Okay, so we write it as, we can also write it as xi equal to phi of x1, x2, x3, where x1, x2, x3 are the components of the reference vector uppercase x. Okay, so it's going to be a little confusing in the beginning, but always remember uppercase means reference, lowercase means deformed or current. If that, you'll get used to it. Okay. So this mapping here, P, the deformation mapping, it's like mathematically speaking, it's also like calling it a function. Function P has to be an one-to-one mapping. It has to be a one-to-one mapping. What does that mean and why? Why should phi be a one-to-one mapping function? What is one-to-one doing here?
So we're not having one particle turn into multiple particles, so it's every.
So like if an atom went from one position to another, it can only go to one position. It can't go to two positions. So it has to be one going to one. Can't be one to many. Right? It has to be such that the atom has to go exactly to one position. It can't split and go otherwise. And you can't have many particles land at the same thing. Each particle should have a unique mapping. Okay. So this one-to-one really talks about uniqueness. That is, you can't create or destroy atoms. So whatever is in a reference position has to be placed somewhere on the deformed configuration. It can't be missed. It can't be added suddenly. Okay. So if that is the case, if P is a one-to-one mapping, then P should be invertible. That is, if P is a one-to-one, if x equal to P of uppercase x, that is, if you are listening to this as an audio transcript, when I say x, I by default mean lowercase. When I say uppercase, I'll say uppercase. Okay. So when x is equal to phi of x, this also implies uppercase x is phi inverse of x. You can invert the function, or the deformation should be invertible. That is the idea. Okay. A time dependent deformation mapping that is P, which depends on uppercase x as well as time, is called, anybody? It's a very common thing that we know. It's just giving a very funky definition. A time dependent deformation mapping is nothing but so come back to the rubber band example. If I just take initial configuration, mark two dots, and then stretch it to a no position, I get an increase in the length. like a mapping went from one point. They were initially here, we call it L naught, and then after you stretch, they went to these 2 points. We'll call this L1. So that is a mapping. This point here has been mapped onto this. This point here has been mapped onto this. Instead of seeing it as a photograph, what if you are doing it in live or seeing it as a video of the points continually moving apart? The deformation, this is at T1, this is at T2, this is at T3, and so on. So if you are watching this point move further and further and further, what will you call it?
Elongation.
Well, elongation, but there's a more basic term to say that. What is it when some point is moving with respect to time? Motion. It's more, this time dependent deformation is nothing but a fancy word to say is called motion. Okay. Now, when we say deformation, we almost always think something is deforming. Deforming means changing in shape. But if you are just moving without having a shape change, that is just like a rigid body moving through. That is also under this umbrella term, time dependent deformation. It's just that the shape change is zero, but position changes happen. So it's a very all encompassing term, deformation mapping, which includes shape change, which includes rotation, which includes linear motion, it includes compression, everything is rolled in here. Okay. So we are going to see an example just to get some, sense for what's going on here. Did you write this? Sorry. So example 3.1. So the real world question always is, we apply load, and if you are doing a simulation, you want to predict the deformation. You want to predict shape change. If you are designing a component, you apply the loading on the component. You are trying to say how the component will change shape during the operation of the machine or whatever. In this chapter, we don't talk about loading. What we do is we directly give you the deformation mapping. Phi will be provided directly. And for now, you shouldn't ask the question, how is this phi achieved in reality? That is the topic of later. Okay. So when we say this, we are going to write x equal to phi of x. That is one way of writing it. Or xi equal to phi of x1, x2, x3. And of course, I runs from 1, 2, and 3 directions. So we are told x1 is equal to alpha x1, uppercase x1, x2 equal to alpha uppercase x2, and x3 equal to alpha uppercase x3. Okay. How will you write this in vector notation? This is like writing x equal to alpha x. So your deformation mapping here is just a constant. What we wrote as P of x in a very general form, in this case, P is a scalar alpha. Actually, I'm sorry. P is alpha times x. It could be more complicated, but it just happens to be a very simple formula, alpha times x. Okay. Now think about what is this representing. If suppose alpha is a quantity which is positive, but less than 1. What does this mean? You take a cube, we always start with the unit cell, because if that unit cell shrinks or bends or twists, it's easy to understand. That is, you start with a cube of side 1 unit each. What is the first equation telling you?
Shape change in x direction.
That is, whatever was at 1 unit is now at alpha units. You have reduced the length by alpha. Same thing in the other direction, same thing in the other direction. So in each dimension, the length has reduced from 1 to alpha. Or if alpha were greater than 1, it has increased from 1 to alpha. Okay, so this is after this deformation operation, that unit cell, which we choose as our reference, is now a smaller cube whose side is not 111, but alpha, alpha, alpha. So this is simple compression or tension depending on what alpha is. So when you talk about loading, where it enters the picture is how you specify this constant alpha. So if you're doing an experiment in a suppose you take a block of concrete and you're crushing it, that would be alpha less than 1. Or if you are taking a bone and you're putting it in a UTM, universal testing machine, and stretching it, that would be alpha greater than. Of course, no, this example itself is slightly unphysical, because if you have a cube, there is no way you can compress all sides equally. The only way to do it equally from all sides is if you drop it under the ocean and allow hydrostatic force to crush it. But that hydrostatic force is also spherically symmetric. It's not along the axis. So this is a made up example. Okay. All right. The other example they have is x1 is equal to x1, uppercase x1 plus gamma x2. X2 is equal to x2, uppercase x2, and x3 equal to uppercase x3. What is happening here? If you take your unit cell, always will take the unit cell because that's the reference configuration. It's the easiest. Along the directions 2 and 3, nothing is happening. So those lengths will not change. But along the direction 1, there is plus gamma x2. What does that mean? So this is going to be one of the types of questions you can expect in the exam. So you start with a unit cell. And you have to do a thought experiment where if this is direction 1, you take any point here. Let's say this is this point here, 1, 0, 0. Okay. This point, according to this equation, if you started with the initial configuration of 1, 0, 0, the x2 direction, you will have the point had 0 coordinates, that is 0, 0. So, okay, bad example, not this point. Take this point here. So this is 1, and this we'll call it axis 2. So this is also 1, and this is axis 3, 0. 1, 1, 0. So this point here, if you subjected this deformation, what will be the lowercase x1 value? In the next instance, this will become 1 plus gamma 1, 0. So instead of the unit cell being at 111, centered at corner at 111, this point is now going to be at 1 plus gamma 1, 0. So this is basically going to be this face alone I'm drawing is going to become like a parallelogram. Hope I'm drawing this right. So this is 1, this is 2. So initial configuration, you have 1 comma 1 comma 0. I'm not drawing the, I'm drawing the plane. Z coordinate is 0. So this point here, according to this transformation, would have now moved on to, from here, if gamma is a positive number, this point would stay right here, but every point would be shifted to the right by exactly gamma units. Right? Every point except this, sorry, including this point, every point is going to be shifted to the right by gamma units. So this is a statement of shear. Shear deformation along axis 1, whereas the other dimensions are all staying put. Okay, so this is pure shear along 1. And as you know, the shear strain will be quantified as gamma. This is the change in length divided by original length. Gamma divided by 1, or just gamma. And this angle, you call this theta, tan theta is equal to gamma, or theta equals tangent inverse of gamma. I mean, all the stuff that you have learned in prior classes. Simple shear. Okay. So I'll tell you the spoiler, which is this whole unit is about how to write out the properties of the deformation mapping and how to use it to express deformation or various quantities associated with deformation. Now, let me ask you a simple question. Here, let's say alpha less than 1. It means that a cube that was initially side 1 in each direction is now side alpha in each direction. So what is the change in volume here? Initial volume is 1, final volume is alpha cube. Okay. What is the change in surface area here? Initial surface area is 6, final surface area is 6 alpha squared. So 6 times 1 minus alpha squared. Not that it's relevant for a cube. What is the change in length of this cube? Initial length is, like, if you think each side has a length of 1, the final length is alpha. So the whole deal about deformation analysis is not just computing this mapping, but that mapping comes with length, area, and volume changes, which we want to work out. How to do that mathematically, that's something we'll see. Not only that, you can also use this to understand what is the nature of the deformation and how to express a certain shape change as a mathematical deformation, or how to take a deformation and visualize the shape change. You have to go both ways. If I give you this, can you draw this? If I give you this, can you write this? These are the skills we want to pick up here. How to mathematically describe something and how to interpret a math equation. Okay. Again, I ask you to read the section 3.2 to kind of supplement this discussion. All right. Can I erase that side? 3.3 material and spatial field description. So if we consider a scalar, okay, you can, what's the property of a scalar? Like how do you define scalars that we talked about in the previous unit? A scalar is, you want to say something, I know. Sure, that is distinguishing it from a vector, but with respect to coordinate transformation, how does a scalar behave? So everything is a number, even tensors are numbers. So how do you define scalar? So I'll give you an example. I'm observing the temperature of a point. I have my own coordinate system and you have your own coordinate system. You are also sensing the temperature of the same point. Will we get different values? No. So can you put that into a definition now? A scalar is invariant to coordinate transformations. That is the idea of a scalar. You can observe it from any point of view or any frame of reference. It will have the same value. Mass is mass, temperature is temperature, pressure is pressure. It doesn't depend on the observer's frame of reference or coordinate system. It's not the case with velocity or position or acceleration. It's true with scalars. So that scalar, okay, example temperature, the book has a funky font, and I don't know if the people who do the book don't understand that we can't do fonts like the book. Okay, so I'm going to write G and I'm just going to put a dash here to denote it is G, but it's a quantity, it represents a scalar quantity. This scalar quantity can be written as G of x comma t, where x is a point in the current configuration, x is a point in the, or I should write, not x is not, I shouldn't write x is the point, I should write x is the position in the current configuration, or we can also write G with a dash is equal to G tilde, this symbol is tilde, G tilde in the reference configuration, where x, uppercase X, belongs to the point, a body in the reference configuration, and X is the position in the reference configuration. So I'm going to introduce two definitions here, which may or may not look obvious right now, but again, stick with it. Slowly, it will start making sense. Some people know this already, so it will look like this is obvious, but for some it's totally new. My advice is persist, persist, persist. Eventually, it will become familiar. Okay. So before we write it out, let's talk a little bit. I like this example where I'm an instructor. I come to this class at this time on Tuesdays and Thursdays. Whoever is here, I teach them. My students of interest are not, I don't know them. I teach whoever that walks through this space at this time. Okay, that type of a description is called an Eulerian description. I am focused on a certain volume in space and I monitor only that volume. I don't worry about what happens outside the volume. In the sense that I know all of you in this time and in this place. The moment you walk out, I don't know you, I don't care about you. Or before 5:30, I don't know where you are. If I abandon that Eulerian disk, if I abandon my interest on the space and actually get interested about you, about right now we have 7 of you. If I track each of you separately, tonight where you go, tomorrow when is your schedule, etc., that becomes what is called as the Lagrangian or material description, wherein you track a bunch of particles and see where they go instead of focusing on where they are. Okay. So I'll try to give some examples from different measurement sciences. If you are familiar with fluid mechanics, suppose you take a velocity probe like a hot wire anemometer, you stick it in a certain volume, certain point in your flow. And the hot wire anemometer basically produces a voltage which is proportional to the fluid velocity at that point. And you read out the velocity as a function of time. You are getting the velocity of one particular point in your flow field. At one instant, there are a bunch of molecules occupying that zone. The next instance, they are gone. Some other batch walks in and you are measuring the velocity of that batch. Gone. Again, another measurement, gone. So you are interested in the velocity of the fluid at that location in space, not necessarily for the same set of molecules. Does that make sense? This is an example of a Eulerian description of a quantity. I am interested in the measurement or the value of that quantity at that point at different times. It can be temperature. Instead of a hardware anemometer, just imagine a thermocouple probe that I stick in the flow and I read the temperature as a function of time at that point. If I want to know the temperature at some other point, what should I do? Bring another thermocouple, put it at another point so that I get a readout at 2 different points, 3 different points, or n different points. Okay, this idea is Eulerian. Eulerian means space focused. I am interested in space at a point, not about matter or material. The other way of doing a fluid measurement is, who knows what is a tracer? Suppose I have a tiny dropper and I have a dye in the dropper. I take it in a point in my water tunnel or wind tunnel and I drop that dye so that the fluid will carry it. And then I take a video. I see a time lapse of the dye getting dispersed in the fluid. So the dye basically follows the fluid molecules. Wherever the dye goes, you know that the fluid molecules are going there. So if you drop your dye at T0 and you observe this for the next 10 seconds, whatever fluid molecules were there at that point when the dye was dropped, they are the ones you are tracking for the next 10 seconds. I'm not interested in that place where I dropped the dye. My focus is always on where are the dye, where are the molecules. I'm tracking each of them. That is the analogy where I said, instead of focusing on who is here, I start tracking each of you individually after you leave or from now until say some time. That becomes material or Lagrangian. So the firm message here, of course, I'll give more examples on solid mechanics also. The first example is human. You are all here at this time in this place, so I'm interested in you. That is Eulerian, space focused. If you go home and I start tracking each of you, that becomes material for Lagrangian. Fluid mechanics example, if I stick a probe that reads out the velocity at a given point, I am only interested in the velocity at that point. In 1 second, in 1 instant, fluid molecules come. I read their velocity, they are gone. I don't care about them. I care only about that point. If you do a tracer, drop a dye, watch the streak of dye go through your fluid, that becomes Lagrangian or tracking. I'm taking a tiny parcel of fluid and watch how that parcel is distributed. It can be divided, like initially you have a blob of dye, that dye is then distributed, it just becomes dispersed in a larger volume. So there are shape changes, there is motion, there is deformation, and all that is described in the reference coordinate. What is the reference here? At time 0, I drop a blob of dye. That is my reference configuration. From that configuration, how does the dye change in shape? That is my interest. That becomes material description. Okay, with me so far? All right. In solid mechanics, most often, if you think about it, you are interested only in the material description. You take a little piece of metal. You're doing any kind of sheet metal work or any kind of metal like manufacturing, like machining. What are you doing? You're deforming the shape of the metal, bending it to shape. You're using a hammer. You're using heat to bend it or make it more ductile and so on. You are always interested in a given amount of material, but you want to change their shape in a certain way. So you are always interested in a fixed amount of material. What you want is to know where each point went. Of course, in the foundry or in the machine shop, nobody is doing math. We do it using mechanical force. We use what we need to do to induce a shape change. The idea is when you are subjecting a solid material to a loading, you want to know where each material gets pushed into, and you want to describe it in terms of where it was initially. Initially it was here, then it got pushed here. Initially it was here, then it got pushed here. So it's always better described in the reference configuration. So Lagrangian description is more natural to describing solid mechanics. If you think about it, you take my experiment. I have a water tunnel. I stick a hot wire anemometer or a thermocouple and I read out the flow velocity. There is some dynamics because there is a flow. Different fluid molecules keep coming time after time. But if I do the same experiment in a block of ice, does it make sense or does it have, it does make sense, but the question is, which is the, so if you stick a thermocouple in a block of ice, you are going to read the temperature of that particular point. Unless the ice melts, there is nothing else to do, right? So there is no real reason to use a Eulerian description for describing solids because there is not much change in position in the current configuration. It's mostly change in shape. Solids are all about change in shape. Fluids are all about both position and shape. That is, you can take a tiny fluid element. It might not only move, but it can also change shape as it moves. So in fluids, this using both is more common, and actually Eulerian description is much more common. Whereas in solids, it's much more suited to use a material description. Okay, so this overview I'm providing because what comes after that is going to be heavily dense mathematical stuff. But before you begin, you should be able to clearly say in simple words what is Eulerian or space fixed description, spatial description, or what is Lagrangian, which is more material focused description. It's about the material, it's about a group. Keep remembering that example. If I'm interested in whoever comes here, I'm an Eulerian. If I'm interested in you, 7 of you, Actually 8 now, since you came back. If I'm interested in eight of you, I'm a Lagrangian. Keep remembering that. Okay. All right, I'm going to provide some of the definitions that the book gives, just for keeping it consistent. G of x comma t provides the quantity at a particular position in space, regardless of which particle is occupying it at time t. Eulerian description provides the quantity. So G of x comma t, that is the Eulerian description, provides the quantity at a particular position, regardless of which particle is occupying it at time t. What I said as molecules is replaced by the word continuum particle. Otherwise, everything I just said is the same. So the variable used here is the spatial variable, lowercase x. So the other thing you need to understand is x is used to denote a position in space. It is to denote a certain point in space. And we are talking about a continuum particle occupying that point. It's the subtle difference between you occupying this room for 90 minutes than somebody who lives here. Of course, nobody lives here. Okay, yeah. So this X here denotes ES308. It is the address or location for a particular point in space. It's not reference to who is here. Okay. Now we'll see the other one. This Lagrangian description is written in terms of material properties not spatial positions, that is, this expression G tilde of uppercase x comma time, G tilde of uppercase x comma time gives the quantity for or of particle x at time t, regardless of where the particle is located in space. So x, lowercase x, is the address of a spatial location. It's the ES308, the address for this room. X here is the position of a certain particle. Okay, that particle, it's a little complicated here, so I would like if you would listen. So you take a blob of material here. Okay, any corner of the eraser, you take a blob of material. When I say it, suppose twist it, the if you take whatever, you can take any little sample, call it your initial particle. When you do your twisting, some of them move, they may move this way, some of them may move towards me. Your particle can be stretched in space. It can span a large volume, and it can also be the case that you might use different, they might occupy different positions in space. That is, when I do this, some particles have gone forward, some have gone towards me. There is at least a centimeter gap between the extremes of your initial particle. So they occupy different locations in space, and that location is denoted using the spatial variable, but the particle itself is a union of all those little points. So another example to think about this is, what is USA? How, I'm sorry. Okay, I think you should allow me to make my rhetorical points. Okay. The landmass USA, how do you define the landmass USA? It is the 48 contiguous states. And then there are two states which are not part of the mainland. They are separate, Alaska and Hawaii. And then there are territories, Puerto Rico, other places. And then there are bases that the US owns in different oceans. And then there is Greenland, where US has a military base. And then there is some place in Philippines where there is a military base. So there is US territory in many places. So if you think of USA as a particle, that particle is distributed across many oceans. Same thing goes with France. If you think about France as a country, you would think it's a European country, right? It's located in Europe. It's actually technically not true. France has maritime borders in every continent because France has territory in every continent. It has territory in Europe, Americas, Asia, Australia. It has territories in Antarctica, everywhere. So everywhere you go, there is French land or France as a territory. So you can think of your material particle as initially it could be it could occupy a little volume, but during the course of deformation, it can stretch out, it can become elongated, and can span large distances, which is like saying the particle X at a time t, regardless of where the particle is located in space. That is, X itself is a position of lowercase x. X is not one point. X is the location of where all particles are. USA is not just one land, it is wherever USA has territory or France has territory. So this Lagrangian description talks about particle X. How do you define particle X? That is the crucial key question which you should understand. How do you define this particle? What is a particle? I just gave the answer, but if you listen to what I said, you should be able to answer this question. How do you define a particle? So you're defining a position, not the particle. Particle is an entity. Define that entity. So I'm going to give you an example to make you push you towards the idea. So you take a blob of very heavy diesel oil. Diesel oil. Take a blob, like take a large droplet, like something that's about 1 millimeter in size, a droplet of diesel oil, put it in water. Diesel is so heavy and viscous that it won't readily mix with the water. It will stay as a droplet within the water. Okay, and if you gently perturb the water, the droplet will just gently do this and still remain as a droplet. Let's consider this droplet as our particle. All the oil that is in the droplet is our particle. Okay. Now gently, let's say I bring to my both hands and I squeeze this droplet such that this droplet now becomes flat as a pancake. With me? This droplet is now flattened as a pancake. Now my particle is still there. It is the same oil, same volume, except the shape of my particle has changed from sphere to a disk. Okay. And now I'll use my hands to kind of mix up the water so that this droplet is now broken up and now it has fragmented into smaller droplets. My particle still exists. It is just fragmented into so many pieces. It is occupying so many locations in space. Okay. Now, when I first started the experiment and I placed the droplet at some location, I have no interest in following what goes on in that location, because what I am interested is where is my oil? The pieces of the each fragment of the oil, wherever they are distributed, I am still tracking them. That is my particle. The particle is the entity which can undergo deformation and even fragmentation, but we are always tracking where the pieces are. That is the particle, and whichever parts or whichever locations which are currently occupied by my material, in this case the diesel oil droplet, that is X. So X itself can be a distribution, it's not a single point. That is the message. Okay. So again comes back to our country example. The country USA started as 13 colonies in the East Coast. Initially, that was only USA. Then it became the entire North American continent up to West Coast. Then it added more states, more territories. So wherever you have territory, it is part of that country. Wherever you have the material that you initially designated as as your particle, is still your particle denoted by X. It can change shape, it can fragment into daughters, sons, it can become separated by great distances, it is still part of the same particle. Okay, remember this. It's a very important concept. So Eulerian description is about space, about a single point in space. Once you define the point, material comes and goes. Lagrangian description is about tracking a certain group of particles or this group of atoms which you call as a particle, wherever they are distributed, and how they change shape, how they deform, and so on. And it is not about space. Regardless of where the particle is, that is immaterial. It is about what the shape is. Okay. So in this example, if G denotes temperature, I can stick my probe at some point in the water tank. I can read out the temperature. I can continue doing that. That will be a Eulerian description of that quantity temperature. If I put an oil droplet at a certain point, and after a while, after mixing the tank, I know my oil is distributed everywhere. If I give you a mapping of where all oil exists, that is a material description. Okay. You have a question? All right. Actually, the next concept is sort of the mathematical version of everything that I said today. So I don't want to start it now. It's about 2 minutes to go. So let's pick this up next lecture on Thursday. Okay. All right. Thank you.